I know I'm starting to sound like a broken record when I say this, but now we're going to get to the really exciting stuff. We have a strong foundation on the general chemical behaviors and properties of molecules. We set that up in our water and acids and bases lecture. We've got a strong sense of where proteins come from and how they're built, how they fold into three-dimensional shapes, and the importance of those structures dictating protein function. And now we've also got a nice foundation where we're comfortable with general ideas of catalysis and how enzymes work to lower energies of activation, allowing biochemical reactions to occur more easily and more rapidly. We're finally now at a place where we can talk about these topics like biochemists, and that's what we're going to do here. We're going to enter the true world of enzymatic biochemistry and begin applying terms and ways of thinking of these ideas that are unique to biochemistry, but all the more important because it allows us to conceptualize how these reactions and how these enzymes are working. So this is the second half of Chapter 6, if you're following along in the textbook. In this first chunk of this three-chunk series, we'll be talking about Michaelis-Menten enzyme kinetics, a unique but important way of thinking about enzymatic reactions. And this will introduce us to some terms: the Michaelis constant, called Km, Vmax, or the maximal velocity, and the catalytic constant, or Kcat. In the next lecture series, well, I should say, covering these topics, Km, Vmax, and Kcat fully, we'll take the first two chunks, and then in the last lecture chunk, we'll talk about inhibiting enzymes and different classes of enzyme inhibition. So in the last lecture, Lecture 4, we covered a lot of ground on enzyme function in general and enzyme kinetics. We discussed thermodynamic favorability and the fact that the universe favors reactions that give off energy as a negative delta G. We talked about kinetics as a general concept of reaction speed, and we gave some specifics to zero, first, and second order reactions. We talked about the energy of activation, delta G double dagger, and that being the energy needed to reach the transition state, a physical, molecular thing that isn't really reactant anymore, but not quite product. And we finished that conversation talking about how enzymes bind to substrate kind of well, and then enzymes work very hard to turn substrate into its best, most favorable binding partner, transition state. So now, hopefully, we have a general understanding of these concepts. If you don't feel very comfortable at this point, you should reach out to me, reach out to someone in the tutoring office, maybe rewatch some key parts of those lectures. We don't really want to enter this next phase of lecture watching until you're absolutely sure you're comfortable with the concepts we've already covered. At this point, though, no matter how comfortable you are with Lecture 4 and all of its chunks, you're probably missing the connection between all of these things, and that's what Michaelis-Menten enzyme kinetics allows us to achieve. Every enzymatic reaction that occurs in our bodies involves in all of the above of considerations of thermodynamics, kinetics, delta G double dagger, transition state, and enzyme substrate binding. What Michaelis-Menten enzyme kinetics does is it brings all of those ideas together in a relatively simple and clear way so that you can tie these concepts into a single story. So let's dive in. In 1913, two scientists, Michaelis and Menten, collaborated to come up with this way of thinking about enzymatic reactions. And it's still, now, over 100 years later, the most widely used way of biochemically understanding non-allosteric enzymes. Non-allosteric enzymes being those enzymes that do not change shape upon substrate or regulator binding. That's what's important there. These are non-shape changing enzymes. Consider the simplest enzymatic reaction we can think of. Some single substrate is converted into some single product. We can think of that, if we remove the enzyme, as substrate becomes product. If we add the enzyme, we can represent this reaction as we already have, which is the enzyme and the substrate are independently in the same space. They come together to form the enzyme-substrate complex. That's where the enzyme gets to work to make transition state, and then once transition state is formed, that transition state collapses into product and enzyme lets go. We can begin adding chemical terms to this. Of course, there is a rate constant of the enzyme and substrate coming together to form an enzyme-substrate complex. And since there's a rate constant for that occurring, our double-sided arrows suggest that this can be at equilibrium, which means there's an opposite and equal rate constant going in the opposite direction, where sometimes enzyme-substrate complex spontaneously falls apart and goes back to being enzyme and substrate independently. We also have a second rate constant, which is the rate constant of the enzyme-substrate complex proceeding to the right and forming product. So we have these different rate constants that we could calculate if we wanted to, representing the three main components of this reaction: enzyme and substrate binding to become enzyme-substrate complex, reversing that and falling apart back to enzyme and substrate separately, or proceeding forward and making product. Once the enzyme-substrate complex does proceed forward, and I should clarify that a little bit and really say once the enzyme successfully makes transition state, there's no going back. The reason why this is not a double arrow is that there is no equilibrium here. Once you make product, you cannot engage in a reverse reaction. You can't go back from product to substrate. And again, I talked about this in the last lecture chunk, but it's a key point. Enzymes recycle. We see that this reaction started with free enzyme and ends with free enzyme. Enzyme is not altered or changed by this reaction, and enzyme recycles to repeat this process over again. Now, if we think of a hypothetical reaction where we keep the amount of enzyme constant, we don't add any more or we don't add any less, the rate of such a reaction would depend solely on the concentration of substrate. Add more substrate, the reaction should go faster. Add less substrate, the reaction should go slower. Not surprising. If enzyme is there and it's constant, the only thing controlling the rate of the reaction would be substrate. Experimentally, we can measure the velocity or speed or rate of this reaction by adding different substrate concentrations to a fixed amount of enzyme and just looking to see how quickly product is formed. So we can add a little bit of substrate and measure the rate of the reaction to give us product in unit time. We could add more substrate and see how much product we make. We can add more and see how fast it goes. And we could eventually graph those results, and we would get a graph like this. We would see that as we increase the amount of substrate, we also increase the speed of the reaction. No surprise there. More substrate means a faster reaction, giving us more product. And in fact, at low levels of substrate concentration, we note that this looks like a first-order reaction. Remember, first-order reactions mean that you can change the concentration of one thing, and only one thing, to alter the rate of the reaction. And that's what we're seeing here. If you start off in this area of this graph, if you add a little bit of more substrate, you get a little bit faster. If you add a little bit of less substrate, you get a little bit slower. And since we're keeping enzyme concentration constant, there's really nothing else you can alter in order to change the reaction rate. So this is a first-order reaction. Only one thing is affecting the rate, and that one thing is the concentration of substrate. But we see that if we continue adding substrate at higher and higher and higher levels, the rate of the reaction maxes out or peaks out at some high level. And then we can continue adding substrate, and we see no change in the rate of the reaction. Up here, at these very high levels of substrate, we are now resembling a zero-order reaction. That is to say, nothing is affecting the rate. The rate of the reaction is what it is, and there's nothing we can do to change it. Imagine we have a substrate concentration right here. If we add a little more, then we don't get a faster reaction, we don't get a slower reaction, the reaction rate doesn't change. If we start off in that same place, I lose my cursor from time to time, I apologize. If we start off at that same place and we add a little bit of less substrate, still the reaction rate doesn't change. Since substrate was the only thing we could modify in the first place, and changing the substrate concentration up here at these high levels doesn't alter the reaction rate, this is a zero-order reaction. The reaction rate is what it is, and there's not much we can do to change it. The example we used in the last lecture were the cars on the Mass Pike going over a toll bridge and passing that toll bridge. And it didn't matter if we took some cars off the line or put some cars on, the rate of that reaction, the rate of that toll plaza was going to stay the same. So what's going on molecularly? What's going on in the tube when all this is being observed? Well, at high levels of substrate concentration, all of the enzymes are saturated. And to be more specific, all of the active sites of those enzymes are fully bound by substrate, and so the active sites are saturated. The reaction is going as fast as it possibly can because every single enzyme is constantly engaged with substrate. Think of this as a car plant. This Toyota plant can crank out a maximum of 100 cars per day. You can think of this plant as a single enzyme catalyzing the same reaction over and over and making 100 cars. That's its maximum rate. That's the maximum productivity of this enzyme. If you delivered more substrate, that is, if you delivered more raw material, more sheet metal, more engines, more tires, more paint, would that boost the number of cars being made? No, it wouldn't. The plant is already going at its maximum capacity. It's cranking out 100 cars a day. You can deliver more raw materials, but that's not going to speed up the rate of the plant because the plant is going as fast as it can already. The same is true for enzymes. When enzymes are saturated and there's more than enough substrate around, the enzymes are going as fast as they can. And adding more substrate, or taking a little bit away, is not going to change that rate because they are at their maximum velocity. So we see that zero-order kinetics occurring here, but we're also appreciating the fact that this is the fastest this reaction can possibly go. No matter how much more substrate you pump into this reaction, it can't go any faster, and so this is our first Michaelis-Menten variable, Vmax. Vmax stands for the maximal velocity of an enzymatic reaction, and it is the fastest our reaction can go. That's often an important thing to know about a reaction, how fast it can go. It gives us some idea of the efficiency of the reaction. But Vmax leads us to another very important Michaelis-Menten value. In fact, it leads us to the Michaelis constant itself, Km. Km is the concentration of substrate that you need to get to 1/2 of the maximal velocity. That's a little bit complicated, so I'll say it again. Vmax is the substrate concentration needed to get the reaction velocity to half its fastest speed. Said more succinctly, as defined in the textbook, Km is the substrate concentration at 1/2 Vmax. So here is Vmax. That's the maximal velocity. And let's think about Km and see if you understand where we're going with this. So using this graph that I've indicated here, and there are some values, so definitely guesstimate, see if you can approximate Km using these multiple choice questions or multiple choice responses on the right. As is on the left. As is usually the case, I'm going to give the answer in about 2 seconds, but I'd like you to pause the lecture, really look at this graph, and try to calculate or estimate Km on your own. So the correct answer to this question is D. If you got that correct, good for you. You've got a really strong handle on the definition of Km. But if you didn't get that correct, be easy on yourself, because this is fairly complicated. Most of you that got it wrong probably went with B, and I'll point out to you right now why that's the case. So this is Vmax, and we'll estimate that to be about a 410 micromoles per second. This is Vmax, the maximal velocity. 1/2 Vmax is about 205, which is where some of you probably got the answer B. So this is 1/2 Vmax. But I defined Km as the substrate concentration at 1/2 Vmax, and substrate concentration is found on the x-axis. So what we need to do is draw an imaginary line to our curve until it hits the curve from 1/2 Vmax, and then drop that line down until it collides with the x-axis. And that point there on the x-axis is roughly 3.5, which is where we get D. Let's do that again. If this is Vmax, we're defining Km as the substrate concentration at 1/2 Vmax. So the first thing we have to concern ourselves with is what is 1/2 Vmax? It's about this value here. But we're looking for the substrate concentration at that velocity. And substrate concentration lies on the x-axis. So we have to drop a perpendicular line down, and wherever that line collides with the x-axis is our Km. That's our Km. It is the substrate concentration needed to achieve 1/2 our maximal velocity. This is shown in your textbook in this figure here as well. So why is Km important to us? Why go to so much trouble to calculate it? Well, Km gives us very specific information about the efficiency of substrate binding by an enzyme. We can understand how well enzymes bind substrate by looking at that Km value. The way I remember it is that it's an inverse relationship. Lower Km values mean better substrate binding. Enzyme likes to bind substrate more the lower the Km value is. Everything we're talking about here only holds true if the enzymatic reaction we're considering is in what is called the steady state. The steady state is when the concentration of the enzyme substrate complex remains constant. That's a fancy way of saying that's when the enzyme is saturated. So in order to do these calculations and in order to get these numbers, we need far, far more substrate available than the enzyme can work on at any one time. In other words, the reason why the enzyme substrate complex concentration remains constant is because there's so much substrate there that every time an enzyme binds to substrate, converts it to transition state, and releases it as product, right there, boom, is another substrate molecule ready to jump right into that open active site. Never do you find free enzyme around, because the moment enzyme becomes free, another substrate jumps in to repeat the process. The textbook goes through all of the mathematical equations and derivations to demonstrate to you that these rate constants are valid for all these enzymatic reactions. You can go ahead and look at that if that's something that makes you happy. We certainly won't cover that in this portion of the course, nor will you ever need to know any of those derivations for any exam in this course. But what it all comes down to when all those derivations is done is this. Oh man, goosebumps. This is the Michaelis-Menten enzyme equation. And this you do need to be familiar with for this course. What this equation says is that the velocity or speed of an enzymatic reaction at any time, and by time I should say at any substrate concentration, is equal to Vmax, which is a constant of the enzyme. It's a property of the enzyme that never changes. Vmax times the substrate concentration you're interested in, divided by Km, another property of the enzyme that never changes, plus the substrate concentration. So in other words, let's say you're curious, I have an enzyme X, and I wonder what the velocity of the reaction would be if I had 10 micromolar substrate for enzyme X. You can calculate that reaction velocity using this equation. Enzyme X has a known Vmax that you could look up or be given. Enzyme X has a known Km that you could look up or you'd be given it. And you know that you're interested in the substrate concentration of 10 micromolar. So the Vmax of enzyme X times 10 micromolar divided by the Km of that enzyme X plus 10 micromolar will give you the velocity of that enzymatic reaction when the substrate concentration is 10 micromolar. It's incredible. Again, this is the Michaelis-Menten equation, and it lets you determine the velocity of any enzymatic reaction at any substrate concentration you're interested in, as long as you know the set constant properties of that enzyme, Vmax and Km. So to summarize what we talked about in this chunk, we first introduced Michaelis-Menten enzyme kinetics as the most widely used biochemical way of understanding non-allosteric enzymes. We then said that the rate of enzymatic reactions depends on the concentration of substrate. At low concentrations, the more substrate you add, the faster the reaction will go. At high levels of substrate concentration, however, the enzymes are saturated. The enzyme is going as fast as it possibly can, and that's Vmax. Km gives us information about the quality or efficiency of substrate binding, and Km is the concentration of substrate needed to get the velocity of the reaction to half Vmax, or half its fastest speed. So Km is the substrate concentration at 1/2 Vmax. We could say this in a little bit of a different way and say that Km is the substrate concentration you need to get to 50% enzyme saturation, and that's where we get at enzyme binding efficiency. If an enzyme binds its substrate really well, you need less substrate to saturate half of your enzymes, because enzymes want to bind to that substrate. If the enzyme's not too happy with that substrate and really doesn't like to bind it so much, you need to pump that much more substrate into the reaction to get to 50% binding. Therefore, the larger the Km value, the worse that enzyme likes to bind to its substrate, and the opposite is true, of course. The lower the Km value, the more substrate and enzyme bind together efficiently. We're going to see what we can do with these values and what more information we can milk with them in the next chunk. But until then, thank you so much for watching.